Okay, now the stage is mine. Welcome to the last talk before lunch and coffee. So I try to be concise. So this work is what I did for my PhD basically, and it uses a lot of data from NOMAD. So we're going back a bit from the large data that we have in Miguel's talk, and we're going now again to small data. But I try to talk about how you can get small data from NOMAD and use it for your own machine learning, whatever endeavors. And I'm going to illustrate some examples that I did. So MADAS is an acronym. It stands for Materials Data Similarity Framework, because I'm using similarity metrics to for two different use cases. That is data quality assessment, and the other use case is finding interesting materials in large databases. So if you want to do a data analytics in any way, you will face some challenges. The first of all is access to data. And I want to illustrate it again with the numbers from NOMAD. You find here there's like about 20 million uploads. And this data, I mean, you can find it through the API or through the GUI, and you have easily access to it. But finding your data is another question, right? You need to find the right query. You need to download the data. You need to get the data into your machine learning pipeline. And this is one of the challenges that you will have if you actually start using this data. The next example is not really a problem, but it's more like the complexity of what we're dealing with, is that within NOMAD we use very comprehensive data schemas. So I brought an example here. Basically, think you want to build a machine learning system that just predicts the total energy of your compound, right? Or you want to divide it by the number of atoms, have the energy per atom. Then you will, if you download the JSON archives from NOMAD using the API, there's a tutorial that you can use to learn how to do this. You will still have to extract the value that you want to put into your machine learning pipeline. And I'm going to show you how complicated that is. So first of all, you have to find the calculation keyword, and then you traverse this. There's a list of different calculations. In this case, it's only one. Then you have to find the energy keyword, the energy key in this dictionary, and then you have to find the total energy, and in the end of it, the value of the total energy. So now, don't get me wrong, I don't think that this is bad in the way the NOMAD schema are built. I think it's just a necessary complexity of the problem. If someone else in another database claims that it's easier in their case, I think they oversimplify the problem and they're just not giving us information, right? But anyway, if you want to do a machine learning thing, you somehow need to get the data out, right? Another problem that you will encounter is the encoding of your material properties. And one example I want to give here is this electronic density of states. So if you want to feed that into your machine learning model, you need some kind of representation that your machine will understand. And in this case, I'm going to use some binary valued fingerprint that I'm going to introduce in a couple of slides. And that's it, right? So these are more or less the problems that you will encounter. And because in my PhD I had these problems, I wrote a piece of software to try to deal with it. And this is MADAS, which I'm going to introduce to you now. So we start first in this diagram here on the right side with data management and the data sources. And the data sources, of course, in the NOMAD project meeting, users meeting, it's going to be NOMAD data, for which there's a native connection within MADAS. But you can also, maybe you want to connect to other databases, right? And this is like Materials Project or AFlow or whatever. And in this case, this is solved by API interfaces. And you might think this is a duplication. API already means application programming interface. But this is an interface to the external application programming interface of the external data source. And this is really just a small Python script or a function that allows you to understand the API of the external data source and extract the data from there. So one example, just you don't read the code, just show you how small this can be. This is an API for the AFlow database that allows you to query the data and get all the atomic structures out of it. Same for the OQMD database or the Materials project. It's done in a couple of lines. And you can use this building block in your pipeline and exchange just the data source that you use. In the next step, we take this, whatever comes out of the material, of the interface, which is a material object. We write those to the database. And coming back to the problem of the complexity of the schemata, the way of getting the value out from the schema into your database is really, again, a function, right? It's a function you can define as you define your API interface. You define, so this one here is get total energy, and it will just traverse this dictionary path and return you the energy in electron volt instead of joule, like they are stored in NOMAD. So this database is using a backend for the file storage, and currently the files that are used are the ASE atoms.dbs, so something that's interoperable, maybe with your existing pipeline. From there, we can now go ahead and start with analysis. And the first part is we start from the database, we extract the material objects from the database, and we compute material fingerprints. So this could be what I've shown you, a representation of a spectrum. It can be any type of descriptor that you want to use. Could be, for example, SOAP, if you're familiar with it, or ACE, or whatever thing. We can use these fingerprints to compute similarity matrices, because this is the focus of the framework, but of course you can use them also for other things. The similarities can go into AI tools, and if I talk about similarity matrices, the AI tool is probably clustering. So this is a use case that we've already used a bit. And supervised learning is yet to be explored, but there's an interface to sklearn, so it's pretty straightforward to also use that. You can not only use the similarities, you can also use directly the descriptor values that are computed for your fingerprints. And of course, if you want to do supervised learning, you need somewhat the material properties that you get from your database, and you can combine everything there. The whole thing is installable via pip, and I will give you some URLs, some links in the end of the presentation. So now, before we can look at any results, let's have a look at some of these fingerprints and how we use them to encode spectra. So a good part of the work was to define these spectral fingerprints, and what you see here is basically the pipeline of creating these fingerprints. And in this example, you have here the electron density of states of the same material computed with two different sets of basis functions with the FHI-AIMS code. And yeah, so in the first step, you just take your spectrum. This is just your input data, right? In the next step, we do a nonlinear transformation to transform this spectrum into a fingerprint. And this fingerprint is a 2D bitmap of the original spectrum, where we can put the focus on specific regions in the x-axis. So in case it's not the energy, you can choose something else, so that this region will be more pronounced in the final fingerprint. And you see the result here for two different spectra. And what you do in the end is you compare these two more or less by putting them on top of each other. And the similarity coefficient that we compute here is the Tanimoto similarity, which is defined as the intersection of the two sets divided by the union of them. In colors, that means you take the purple bits and divide their number by the purple bits, the blue bits, and the red bits combined. And this gives you the similarity coefficient, which you can then use for whatever analysis in the following. Okay. So with that, I hope there's no immediate questions. We can go ahead and start with data quality assessment. I think I'm actually pretty fast. So the first use case is finding interoperable data. And for this, we use a dataset that was made as a benchmark dataset for FHI-AIMS, for the FHI-AIMS code. So it already contains all the data, all the density of states computed with different number of basis sets, specific number of k-points, specifically in order to benchmark the performance of the code. And what we did then is we computed the density of state fingerprints for all of them, and basically what you've seen in the slide before. And now this matrix shows you the similarity coefficient for all of these different materials. So we have about 144 compounds, different calculations for the same material. And each of the pixels in this matrix basically represents the similarity coefficient, where blue is a low one and red is a high one. And yes, so this is a symmetric matrix, and you see on the diagonal that the similarity of each spectrum to itself is always 1. Okay, so why is this interesting? Now, what we did is we sorted this matrix by the mean similarity. So the index used for figuring out which calculation goes where is simply the mean of each of the columns or rows respectively, and this gives you this curve of the mean similarity. And we just sort all the data based on this, based on the mean, and it gives you this very nice block structure. So if there's a nice block structure, that tells us there's something to be explored here. And what we did then is to compare this with the number of k-points that were used and the number of basis functions that were used. For anyone who's not doing DFT, these are the two most crucial ones if you want to think about the electronic structure. So no surprise here, but this is also why specifically we look at them, right? And if you look at this data, you see that there's a clear correspondence between these blocks in the matrix and then the blocks in the k-points. So in order to find the block structure, we only use the matrix, not these ones. If we now go through these blocks, I show you here also the density of states of the compound that's very much to the left. And if you look at it, you already see that it's highly underconverged. So yes, like all these delta-like peaks in there, indicative of too low a number of k-points. And there's even this very suspicious looking feature here that we don't really know where it's coming from. And if you look at the block that corresponds to these calculations, you see that all of these are the ones with the too few k-points. So we have like 24 k-points, I think, times some factor. Yeah, and you see that basically no matter how many basis functions you choose, if you choose too few k-points, the results will always be dissimilar to the higher converged ones, which is to be expected. What is more interesting, though, is that we found another block that has almost the same structure as the first block. So there's still no k-points, almost like very few k-points used, but the number of basis functions change. But this one has a higher similarity to the rest of the data. And what happened here is, after we looked at the original data, is we found that for these calculations, they use a scalaristic approximation for the relativity of the core electrons, and for treating relativistic effects. And these, if you use them with too few k-points, introduce these very suspicious features. But if you increase the number of k-points, these disappear. So it's not a problem for the accuracy of the code, but it's still interesting. You find some numerical noise in there. Okay, so let's take a look at the next block. So the next block, if we look at the data, we find that here all calculations use very few basis functions, but they might use any other value of possible k-points. So we see this block is highly similar to itself, but it's also not very similar to the rest of them. And you see this calculation, and see this is already much more smooth. So here I choose the one with the highest number of k-points, and it almost looks like a real spectrum. But if you compare it to the one that's actually at the very top, that uses the highest number of k-points and the highest number of basis functions per atom, you find that actually the features look pretty different, especially these little peaks here. And this confirms what we already know. If you choose too few basis functions, you cannot represent your Cohen-Charm wave functions effectively in your code. Why is this interesting? You say this is already known. It's interesting because here we didn't use any physical knowledge so far. So it's really just coming from the data. You don't need to know anything about the data. It's just if you have a convergence process and you have a lot of data available, all the converged calculations will be many, and they will be similar to one another, which may allow you to find settings that are interoperable, but still don't have to be at the highest level of accuracy. Okay, and And now I promised that there are that this is a pipeline that you can exchange different parts and you can adapt it. And actually, this is implemented. All this example is implemented in a Jupyter notebook. So what you can do is you just go ahead and replace this query to the NOMAD database for another material, and you end up with the same plot. You can exchange the fingerprints with another type of fingerprint, and you can end up with the same plot. And all of this allows you to pretty fast develop your own analysis methods. So there's a link to this also in the end of the talk, and it's also here. So, okay. Next, finding similar materials. It's a short example, but it comes with a most interesting question. So for any material, which other materials are most similar to them? It's basically, when you look at a large amount of data, maybe it's one of the first questions that you might ask yourself. So in order to answer this question, we went to NOMAD. We picked 1.8 million materials that had electronic density of states. This was big in 2019, I think. So this data clearly has changed, but as you will see, we computed all pairwise similarities. So we literally compared all unique pairs of fingerprints, giving us a huge matrix of size 1.8 million times 1.8 million divided by 2. We have all the unique ones. And with these, we can search for the most similar materials, but you just go through the row and see what are the highest similarity scores. This is also why we didn't repeat this so far, because the computational effort of computing this huge matrix is actually quite large. But there might be some methods to accelerate this, which we will explore in the future. So what do we find? In this example, we're looking at gallium arsenide, which is a very well-known semiconductor. I guess everyone has heard of it. And in this plot, you have the distribution of the similarity score that we computed with these fingerprints. And first of all, what you see if you look at this data, so first, though, this is the similarity score, the Tanimoto coefficient, and if 0, the materials are absolutely dissimilar, and if it's 1, they are identical. And you see that basically the highest amount of them is actually pretty dissimilar, right? So it's pretty heterogeneous. And also note that this is a logarithmic scale, so this is actually quite a few compounds. And if you go down this all the way to the end, and you look at only the higher ones, you find these are very few. So basically, it's actually just 3 of them. And so we can look at them, all of them individually. So what we find, so the gallium arsenide is the original curve, is the black one, it's in the background. You can't really see it because all the other ones are pretty much on top of it. What we find, to not so much surprise, is that the most similar material is gallium phosphide, and which contains phosphorus as an isoelectronic substitution of arsenic. So it would be expected that the electronic density of states will be similar among these. And here we actually show that this is the case. But what is more interesting is that we also have this lead carbide and the sodium, boron, germanium, which do have similar crystal structures, but they would be something that you probably didn't expect in the first case, right? But if we look at the density of states, especially close to the Fermi level, you find that all the shape of the DOS is actually pretty similar among these. Yeah, and this basically allows you to scan large databases and find new entries and hopefully discover new physics that you did not expect in the first place. So with this, I'm going to wrap up because I think everyone is interested in lunch. What I've shown to you is data analytics with fair data, and this example that I've shown you are these schemata used in NOMAD. I've shown you the MADAS framework and how you can go through the fields of the databases and extract all the values that you need. I've shown that you can use similarity values for data quality assessment, and I've shown you that you can use it to find similar materials. With this, I want to acknowledge Claudia Draxel and all my other co-workers, and funding from Fonda, FAIRmat, NOMAD CUE, and NOMAD. And these are the references.